Welcome back to Principles of Engineering. Today we're talking about electricity, and this is our presentation for Module 1.2.3, Introduction to Electricity. So if you would go ahead and navigate to your Canvas page and open up your student-guided notes, those will help you to keep track of the information as we go through the presentation. Obviously, you can pause this video at any time to get caught up and replay. If we talk about electricity, what we're really talking about is electrons moving through an object, and that's an invisible force, and it can provide light, heat, sound, and motion. It is a way of converting energy, essentially, from mechanical to electrical back to mechanical. That's the most typical application that we see for electricity. Conversely, we can go from a mechanical primary source or even a chemical primary source, convert that into steam, thermal, turn that into mechanical, rotate, turn that into electrical, generate, transmit that to your house, and then bring it back in and turn it into things like light, motion, as well as heat. So that's electricity in a nutshell. Well, when we look at it at the atomic level, it's interesting to look and see some of the corollaries between the things you learn in chemistry, the things you learn in physics, and the things we apply in electrical engineering. When we talk about a particle at the atomic level, we're looking at elements, and that's the simplest form of material. Elements here in the periodic table. They're arranged by properties, as you've learned in chemistry, of how they react and interact with each other, as well as atomic mass. So when we talk about the atom, that's the smallest piece of an element that has all of the properties within that element. So at an atomic level, when we look inside of the atom, and this is using this is only going down to the electron and proton level, but if we look inside an atom, what we're going to see is in the middle of the atom, we have the nucleus. And in that nucleus, that's where the protons and the neutrons, represented by the red and blue balls, are. The protons are positively charged atomic particles. The neutrons have no charge to them at all, or uncharged atomic particles. So that's the nucleus of the atom. Now, hypothetically, we think about an electron orbiting around that nucleus. So the atomic number is represented essentially by the mass, or the amount of material in the nucleus on that, and that's basically equal to the number of protons in the nucleus. And that atomic number identifies the element within the periodic table. Now, in this example, the question is how many protons are in this nucleus? And it's 3, has an atomic number of 3. So the electrons are negatively charged particles orbiting in a cloud or in a ring or a sphere, however you want to imagine it. They're orbiting around the nucleus. Now, in 3 dimensions, looks something like this, theoretically, hypothetically. There is an area of orbit where they move around the nucleus of the atom. Now, it's not to say that they're in a defined orbit like a planet around the sun. They're just in an area. And when we talk about that, we can shrink this model down into 2 dimensions, just like we do with our solar system. And we can start to talk about relative energy levels with electron orbitals. Now, the difference between an orbit and an orbital is the orbital is an energy state of the electron. It's not a physical location. And as an example, I can't say definitively that this electron is exactly there at any point in time. So when we look at the valence electrons, those are the electrons at the outermost ring on the particle. And when we're talking about this, we're really talking about the outermost energy state. So there's several different representations, and you've learned some of these in chemistry, or you may or may not have learned this yet. But, you know, we've been looking at this for a long time, and really it started out by classifying how elements interacted with each other and then their atomic weight. And we started to come up with basic models that describe the structure. Now, the structure of the atom gives its physical properties, things like conductivity, thermal or electrical. Also, how reactive they are. What do they try and do? Why does oxygen scavenge electrons? So the first model that we'll look at here is the Bohr model. And the Bohr model basically says that these electrons are arranged in rings outside of the nucleus, kind of like a planet system. Well, when we look at that model, we pretty quickly realize that's not really true, because we can't say that these electrons are evenly split around in this specific ring. That's just not true. So now we look at electron cloud model and we say there's a certain probability that the electrons are at a specified energy state. So there's a region where the electron's likely to be found, which leads us to quantum mechanics. And quantum mechanics basically just says that we can mathematically start to describe these interactions at a nanoscale level, and we can talk about the energy states that it required to elevate electrons to different basic energy levels. So that's quantum mechanics. We're not going to go too far with that, but we're going to focus mostly on the Bohr model here. So it's kind of an important thing to start to talk about science here. And just because we can't see it doesn't mean that we can't figure out what's going on. And a classic example here is when we talk about the Heisenberg principle. It just says that the act of observing alters the experiment. So each of these models is useful to describe how an element interacts with the outside world, but none of them are completely accurate. So when we look at the outermost ring, that valence, that has a real big influence on how an atomic level structure or an atom interacts with another atom. So we're going to use the Bohr representation of the atom, and we're going to describe its interactions electrically using the number of electrons in the valence shell, or the valence energy level. So periodic table, nothing new here, except when we start to look at things, we can understand how elements interact by the rows and columns that they're represented in. So we start out here with atomic number 1, hydrogen, and over here, helium, atomic number 2. As we go down all the helium down this row, what we see are noble gases. They all react similarly. We also see commonalities in the number of valence electrons. So from this, we can predict and identify an atom's properties. Specifically, we're looking at conduction, electrical conduction. So at the atomic level, when we look at the number of orbits on an atom, we can predict that. And remember, these are not physical rings, they're energy levels. And the way that we can predict this is we can say that the maximum number of electrons in any orbital is going to be 2 times n squared, where n is the orbital number. So the orbits fill generally closest to the nucleus. And when we talk about these energy levels, the orbit numbers, we break them down into sublevels, S, P, D, and F. And the sublevels aren't really in this image. The sublevels overlap. So example, like the 3D sublevel is at a lower energy level than 4P, and those fill in a different characteristic. We're not really going to concern ourselves with this because we're mostly looking at the valence level. But the valence level can never have more than 8 electrons. So when we start to look at these different electron levels in elements, we can see that the second level, or the second orbital, is going to have 2 times n to the second, which would be 2 times 2 to the second, or 8. Similarly, 18 for the third, 2 times 3 squared, 32, 50, 72. Now, as we get heavier and heavier elements, we get more and more total electrons. Now, this is predicated on the atom being electrically neutral, which says that the number of protons, which determined its atomic number, is balanced by the number of electrons. generally true for the things that we're looking at in this class for conductivity. You can have ionically charged particles where they're more positive or more negative, but they're not necessarily stable particles. So the valence orbit, max can be 8. Now, fun fact about this, in the valence, we want the ring, or we don't want it, but the particle wants the ring relatively filled or relatively empty. Now, the slide says empty or full. Yeah, it would rather be empty or full. Those are stable valences. So in this valence, copper, atomic number of 29, you can see that you have 1 valence electron. Based upon 1 valence electron, we can say that this is a conductor. Now, as we get more and more valence electrons, the atom becomes more and more electrically stable. So an example here is sulfur, 16. You can see that it has 6 valence electrons, which makes it very stable and also makes it not want to conduct electricity. So it is an insulator. Copper with 1 valence electron, conductor. Sulfur with 6, insulator. And the reason for that is because the way electricity flows at the atomic level. So if we looked at an electron flow at atomic level, what we'd see is as an electron moves from one atom to the next, it essentially knocks the electron off. That's conduction. Now, when that atom loses the electron, it seeks another to fill the vacancy. So if we were to look at this, and here I've lined up 4 atoms, you'd see that I have conduction going on, or the transfer of electrons. Now realize that a single electron has got very, very little energy. I believe it's 1.602 times 10 to the negative 19 coulombs. But if we have millions and millions of atoms aligned, all losing an electron simultaneously, we have now got current flowing. So conductors versus insulators. In a conductor, the electron flows easily. Insulator, it's difficult. It takes much more force to make the electron flow. Conductors have 1 to 3 valence electrons. 1 to 3. Good conductors, copper, gold, silver, have got 1 valence electron. Insulators, 5 to 8 valence electrons. Here's some examples of conductors and some examples of insulators. Now, if we were to go into the periodic table, we'd see these share properties by row and column. So looking at this picture, you'll see that there are conductors. Those are the metallic things. Most metals conduct. And the insulators, the plastic. So this surrounds our world. In our houses, this is what keeps electricity in the wire and out of your body. So fun fact, you are a poor conductor because you're made up mostly of water, which is a poor conductor of electricity. So when we talk about electrical circuit, what we're going to talk about is, when we say it's a circuit, it just means that there's a complete path for electrons to flow. That means that we have got some kind of conductive material from a power source returning to that power source, or a circuit. We talk about the properties of an electrical circuit as voltage, measured in volts, abbreviated by V, current, measured in amperes or amps, abbreviated with A, and resistance, measured in ohms, abbreviated with the symbol omega. So the closest analogy, and it's not perfect for you to initially learn about this, is to think about water pressure in a pipe with a faucet. So the analogies, electrical analogies, are the tank of water that's providing the pressure. That's my battery. The pipe, that's my wire. The faucet, which turns the water on and off, is my switch. Now, it's an imperfect comparison, but let's talk about the flow of electric charge. That's measured in amperes. It's defined as 1 coulomb of charge flowing per second. Now remember, I said 1 electron provides 1.602 times 10 to the minus 19 coulombs. So it's a whole bunch of electrons flowing. So if the faucet is off, is there any flow? No. And that's the equivalent to the electrical circuit switch being off. When I turn the switch on, then there's flow. The water flows. The current flows. So current in a circuit, when it's off, my switch located right here is open. It doesn't finish the path. The path is broken right here at the switch. When I close the switch, I have current flow, and the current is flowing through the light bulb, producing light and returning back to the battery. So this is kind of an important idea. Remember, we talked about current is the flow of electrons. And you probably learned way early in earth sciences and other classes that opposites attract. So if I have a negative charge, it's attracted to the positive pole of the battery. And that is, in fact, true. That is the electron flow model. It says that electrons flow from the negative side of the battery to the positive side of the battery. So that's what you talk about electron flow in physics. In engineering, we talk about conventional current. And we talk about conventional current, we say that the current flows from the positive side of the battery to the negative side of the battery. It's not really correct, but we've stuck with it. So it doesn't really matter which way we say the current flows. So for our sake, we're going to say the current is flowing from the positive side to the negative side, and we're doing a direct current circuit, meaning that our polarity never oscillates back and forth. We'll learn a little bit more about that towards the end of this unit. But it doesn't really make any difference which way you go as long as you're consistent. So we're going to use conventional current flow. So let's talk about voltage. Voltage is the force or the pressure that's causing current to flow. That's measured in volts. So you can think about this if this was a water tank, that's my battery again. The water pipe is my wiring. The faucet is the switch. If I had more water in the tank, I'd have more pressure in the pipe. So when the faucet is off, is there still pressure in the pipe? Yeah, absolutely. It's just sitting there. If I open the faucet, is there still pressure in the pipe? Yes, that's what's pushing the water through. So voltage is the pressure pushing the electrons through the circuit. So voltage in a circuit, if I look at the exact same circuit, when my switch is off, I still have voltage present across the battery. When it's on, I still have voltage across the light bulb. Now resistance is the resistance or opposition to current flow. All material has some opposition to it. The electrons, it takes energy to push them out of their orbit and make current flow. The amount of energy that's required is the resistance. So in other words, the resistance to current flow, it's the opposition of current flow measured in ohms. So if I look at my pipe here and I stick a rock down it, the rock is going to restrict or resist or oppose the current flow. So what happens to the flow of water in a pipe if I stick a rock in the pipe? Well, the flow diminishes. And that's exactly what happens for resistance in a circuit. Higher resistance, less current flow. So here I have my light bulb on, light bulb shining bright, and if I stick a resistor in that creates resistance, plug that in line, what I'll see is my light will diminish. It will get less bright because there's less current flowing through it. Now we'll learn about how we mathematically compute that here in our next lesson. So let's talk about measuring voltage. The way we measure voltage is we measure across items. I can measure across the battery, across the switch, across the resistor, or across the light. The first step is to set a multimeter, and this is a multimeter is nothing more than a meter that measures voltage, current, and resistance. Set it to the volt range. In this instance, we're using 20 volts. It's a 9-volt battery. Measure across a component. So if I measure across the battery, in this instance, you've got the plus on the red lead or the positive and the negative on the negative. It doesn't really matter, to be honest, as long as you're consistent again. You'll get a negative reading if you read it backwards, but you can always deal with that. So I can also measure the voltage across a switch, the voltage across a resistor, and the voltage across a light. Notice the circuit is energized to measure voltage. It has to be. So this multimeter idea is nothing more than an instrument that measures voltage, current, and resistance, volts, amps, and ohms. That's what we'll use in our shop. So to measure current, what I have to do is set my meter to the amp range. Now we're DC in this example, so it would be ADC there. And I have to measure the current flowing through the meter. So I have to interrupt the circuit. So in this instance, I take the wire out between the switch and the resistor, and I connect my meter. Again, the positive side lead, the red lead, to the positive side of the circuit, the black lead to the negative. And now the current's leaving the circuit, going through the meter and back in. That's how I measure amperes. Really important that you're in the proper range and that your leads are in the proper position. Okay, to measure resistance, it's a lot like voltage, except it's an unpowered circuit. So I set the meter to the ohms range. Measure across the component, but first remove power. So I take the battery out, and now I can measure across the switch, across the resistor, and across the light. So Ohm's law basically just says that the current through any element varies in proportion to the voltage applied across it and is inversely proportional to the resistor's value. That mathematical relationship between current and resistance applies in all types of circuits. If you know two of the three, you can solve for the third every time. So voltage is V, current is I, resistance is R. This relationship, V equals I times R, allows you to develop all the other ones. So if I knew I and R, I could find V. If I knew V and R, I can find I. I is V divided by R. And if I know V and I, voltage and current, I can find resistance. It's represented by this chart. Just cover up the quantity that you don't know. So if I want to solve for V, put my thumb over V, and I see it's I times R. If I want to solve for I, cover up I see it's V divided by R. Similarly, solve for R, cover up R, and it's V divided by I. So a simple application of this, and then we'll pause with part one, is if I take a flashlight and it has a 6-volt battery and the bulb has a resistance of 150 ohms, how much current is going to be drawn from the battery? I can draw the circuit. Now notice over here on the left-hand side, this is the symbology for a battery. A DC power source. 6 volts is the voltage total. The resistance is just that one element, 150 ohms. So by Ohm's law, if I cover up my I, which is what I'm trying to solve. It's V divided by R. And I plug that into my equation. I get 6 divided by 150, or 0.04 amps. Now that's 40 milliamps, because 1,000 milliamps is equal to 1 amp. That's just basic unit conversions. I could also write that, and I would be correct to say it's 0.04 amps. They're equivalent terms. So we'll pause there with part 1 and pick up part 2 next. Welcome back. We're talking about electricity again, and we're talking about the second part. We're going to deal quite a bit more in Ohm's Law. So just as a quick refresher, Ohm's Law just says that the voltage is proportional to the current flowing through an element times its resistance. So when we look at different circuits, we kind of have to consider how we apply that. And the terms that we use are a series versus a parallel circuit. And when we look at a series circuit, we can see that the elements represented by these rectangles are all connected end to end. Doesn't matter what the element is. It could be a battery, a resistor, a capacitor, anything. But the important note here is there's only one path for the current to flow. So a series circuit has a single path for the current to flow. Now in a parallel circuit, there are multiple paths for the current to flow. So my elements are all interconnected on their ends by a wire. So the current can flow down any one of these paths. So that's the fundamental difference between a series and a parallel circuit. Now when we apply these, what we're going to do is we're going to look at two different laws, Kirchhoffs laws. The first is Kirchhoffs Voltage Law. And all that says is that the voltage drop across each component in a series circuit adds to be the total applied voltage. Now in a parallel circuit, there's a corollary, and that's called Kirchhoffs current law. That just says that the total current in a parallel circuit has to sum the individual branch circuits. So let's look again at our series circuit. So here we have a series circuit, and what we have is a path, single path, for the current to go through the battery, through the first light bulb to the second light bulb. And in a series circuit, if I interrupt that path anywhere along, the current stops flowing because the circuit is open or broken. Now in a series circuit, the current flows through every component and it's equal. And all that's saying is I sub t, represented right here, flows through R1, resistor 2, R2, resistor 3, R3. Now Kirchhoffs voltage law says that the current flowing through the resistance makes a voltage at resistance 1. It makes a voltage at resistance 2 and a voltage at resistance 3. And if I add the voltage at resistance 1 plus the voltage at resistance 2 plus the voltage at resistance 3, it equals my supply voltage, so VT. So let's do some math on this. So let's look at this series circuits, and let's solve it by calculating what the total resistance would be, and then the total current flowing through, and then the voltage drop across each element, and verify the result. So first we need to look at the total resistance. And the total resistance in a series circuit is nothing more than the sum of all the resistances in the circuit. So my RT is R1 plus R2 plus R3. Now an important note here. You're going to see that this is given as 1.2 kiloohms, 220 ohms, 470 ohms. Now I either need to stay in kiloohms, or 1200 ohms is what 1.2 kiloohms is, or 1.2 times 10 to the third, or I need to stay in the base of ohms. So I'm going to stay in the base of ohms on this. So when I add these up, I get 220 plus 470 plus 1200. That adds up to 1900 ohms, or 1.9 kiloohms. Now the current through each element is IT. IT is VT divided by RT, or 12 volts divided by my equivalent total resistance. What I get is 0.063 amps. Or, sorry, 0.0063 amps, or 6.3 milliamps. So if I divide by kilo ohms, I get milliamps. So since it's a series circuit, that current total is the same flowing through each element in the circuit. So let's look at V1. V1 is the voltage across the resistor R1. That's nothing more than I1 times R1, or 6.3 milliamps times 220 ohms, about 1.4 volts. V2 is that 6.349 milliamps times 470, about 3 volts, 2.984. And V3 is 7.619. Now let's pause for a second and talk about this. Notice the voltage drop was proportional to the resistance. R1 is the smallest resistor, lowest value. It has the lowest voltage drop. R2 is next. R3, the biggest resistor at 1200 ohms, has got the biggest voltage drop. So that voltage drop is proportional to the size of the resistance in the series circuit. So let's verify. Kirchhoffs voltage law says the sum of the voltage drops needs to equal the total voltage, or VT should be V1 plus V2 plus V3. If I add these, I end up right at 12 volts. Now, a little bit of caution is in order here. Depending on where you round and when you round, it may not exactly equal the source voltage. In this instance, the digits work out, so it equals it. So Kirchhoffs voltage law, again, just says that the source voltage, 12 volts, is distributed proportionally to the inverse of the resistance. All of the voltage drops through a series circuit, Kirchhoffs voltage law says has to add up to be the source voltage. And it did. Okay, so let's look at a parallel circuit. This is more, in this circuit you've got more than one path for the current to flow. You've got two paths in this particular one. And basically it just says that if there's a single component removed in the circuit, well, the current still flows through the circuit. Now this is a little hard sometimes for students. And all that in a parallel circuit, that when we look at the resistance, we can say that the total resistance, the reciprocal of the total resistance, is the sum of the reciprocals of the individual resistance. So the total resistance, RT, 1 over RT, is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So let's back up to our water pipe analogy. If I had water flowing through a pipe, and we'll call it IT, the amount of water that would go through the tightest resistance here would be the least, and then more, and the most. But the sum of all those water flows has to be more than the resistance that flows through the smallest resistor. So every time the total resistance on a parallel circuit is going to be less than the smallest resistor in the circuit. Now I can do a little bit of math, and I can flip this around and say that my resistance total now is equal to 1 over the sum 1 over R1 plus 1 over R2 plus 1 over R3. So think about that equation for a second. All that this says is my total resistance is always going to be smaller than the smallest resistor that I have in the circuit. Now Kirchhoffs current law says that the sum of the currents in each branch, so the current going down through resistor 1 plus the current going down through resistor 2 plus the current going down through resistor 3, is equal to the total current coming in here at IT. That makes sense too. Okay, let's do a parallel circuit. Same strategy. find the total resistance, find the voltage across each element, find the current flowing through each component, and then verify. So first, the total resistance. What I need to do is to use my formula for my total resistance. RT is 1 over R1 plus 1 over R2 plus 1 over R3. I insert my numbers and solve. Now, be a little bit careful when you type this into your calculator. You'll have to be sure that you get parentheses correctly on this. And the way this would type in would be 1 divided by parenthesis, open parenthesis, open parenthesis, open parenthesis, and then a parenthesis around over 1 over 470, another one around 1 over 2K, another one over 1 over 3.3K to add those up. So be careful of your order of operations. But your sanity check is, I know it has to be smaller than 470 ohms, don't I? It has to be. And there I end up with about 350 ohms when I solve that. Now the voltage across each component is going to be equal to 15 volts, because there's my source voltage. That voltage is applied at R1, at R2, and at R3. So what I can now do is I can find the current through each component. So I'll solve that by saying the current through resistor 1, or I1, is going to be equal to V1 divided by R1, using Ohm's law. So this is 15 volts divided by 470 ohms, or about 31.915 milliamps. We'll call it 32 milliamps. I2 is going to similarly be the voltage across R2, 15 volts, divided by the resistance R2, 2.2 kilo ohms. That'll be about 6.8 milliamps. I3, 15 volts divided by 3.3K, or about 4.5 milliamps. Now my I total would be 15 volts divided by my RT, or about 43 milliamps. That's the source current. Now Kirchhoff just said that IT has to equal I1 plus I2 plus I3. And if I carry the digits back out, 43.278, 31.915, plus 6.818, plus 4.545, all in milliamps, I end up with 43 milliamps equals about 43 milliamps. Again, you may see small errors in here depending on how and where you round. Now the reality is we rarely see a pure series or a pure parallel element. We most frequently see combinations. So the question comes up, what would happen if I pulled out light 1? If light 1 was removed, what would happen? Yeah, light 1 was pulled out, the circuit would be open. All the lights would go out. If I removed light 2, I'd still have a circuit through 1 and 3. If I removed 3, I'd still have a circuit through 1 and 2. Now our last topic we're briefly going to talk about is power in electricity. Power in electricity is the rate of my current flow, or my amperes, times the voltage. So voltage is times current is power, and that's measured in watts. Now that's volt amps. Volt amps. So I need to be in a volt relationship and an amp relationship. If I'm in a milliamp relationship when I multiply it, I get milliwatts. If I'm in a kilowatt scenario, I either had kilovolts or kiloamps as the inputs there. So we have to pay attention to our factors of 10 as we multiply those out. That's it. P equals V times I, or I times V. Now, you may have noticed I could also make these relationships relative to resistance, couldn't I? If I only knew V and R, I know that I equals V times R. Well, then my power would be V squared divided by R. If I only knew I know that V is I times R. Then the power would be I squared times R. So I can use that same Ohm's law in my power relationship as well. That's it. Thanks for watching. Next up, we'll do our lab.